Welcome to Lesson 8, Diffraction, Interference and Spectra. Today we'll point light at slits and gratings. Here's the plan for today. Start with light through a single narrow slit. You don't just get one bright band, you get a diffraction pattern. The central maximum is the key feature here. It's bright and it's twice as wide as any of the others. Flanking it on both sides are dimmer maxima, and they get progressively fainter the further out you go. That wide, bright centre with fading fringes is the single slit signature. Now the double slit, or Young's slits, one of the most important experiments in physics. Light passing through two coherent slits produces a set of evenly spaced bright and dark fringes from the two beams interfering. The equation we need is W equals lambda d over S. The fringe spacing W equals the wavelength times the distance to the screen, divided by the separation of the slits. This experiment was strong evidence for the wave nature of light, because only waves can interfere like this. You simply can't explain those fringes with particles. We also want to note when the bright spots occur in terms of path difference. This is when the path difference, delta S, is a whole number of wavelengths. Delta S equals m lambda. This means that we have constructive interference, so a peak meets a peak and a trough meets a trough. This only happens with a whole number of wavelength difference. Now we take that idea and use not two slits, but many, even thousands, and you have a diffraction grating. The many slits sharpen everything up. Instead of a diffused, spread out peaks, we get bright, sharp, widely spaced maxima instead of soft fringes. The grating equation is d sine theta equals n lambda, where d is the grating spacing, which is just 1 over the number of lines per metre, big N, and small n is the order of the maximum, starting with 0 in the middle and increasing as you move outwards. Because the lines are so sharp, a grating lets you measure wavelength very precisely, far better than a double slit can. A common exam question is determining the maximum number of dots you can see on the screen. Since the angle theta is a maximum at 90 degrees, sine of 90 equals 1, so then we get n equals d over lambda. With this n, we must always round down to the nearest whole number. With this number, we then double it for the number of dots on the other side, and we add 1 for the 0th order. Make sure you remember this. Now, spectra. We study spectra because the light that a thing gives off tells you largely about what it is. This is a lot of how astrophysics works. A continuous spectrum contains every wavelength, blending smoothly. You can get this from hot, dense solids like a filament lamp. A line emission spectrum is a set of discrete bright lines produced by excited gas atoms dropping between their energy levels. Remember lesson 5. And because every element has its own unique set of levels, those lines are effectively the element's fingerprint. A line absorption spectrum is the mirror image, a continuous rainbow crossed by dark lines, where a cooler gas in front has absorbed exactly those wavelengths. This is how we detect nebulae in the universe, for example. Finally, a few definitions to keep straight, because questions test the exact wording. Monochromatic light is a single wavelength. A laser is the classic example. Coherent light has constant phase relationship between its waves. And white light is a mixture of all the visible wavelengths together. These aren't interchangeable, so use the precise term the question's after. And that brings us to the end of the video. I hope you enjoyed, and next time we bend light through glass and then trap it inside a fibre, the physics that carries the internet. Thanks for watching. Check out my tutoring page below.